Dr. Rather.
Thank
Welcome.
you, David.
Thank you.
I appreciate very much David's comments. The symposium that we had was, much to my amazement, quite successful, and it was largely due to people like David and Linda, who jumped in with both feet, and John Preston back in the back there, who is the President Emeritus of Tennessee Valley Interstellar Workshop. And so I'm eternally grateful for that. Ken Roy is here somewhere too, and there he is, way in the back. He's a very shy guy. He's probably back, but he is a major part of the TVIW operations. If you don't know, TVIW is a 501c3 educational organization here in town, Tennessee Valley Interstellar Workshop. And these basically are people who founded it in the first place back in 2011, I think it was. And so it's gotten to the point that they're sponsoring a symposium every year or 18 months. And we kind of elbowed our way in and put in an extra one after only 11 months. And they've been confused ever since. So there we are. I am going to try to pay heed to the great people who made it a success. We had 36 speakers, and I've never looked at the videos of a whole program like this one, 3 days, and so help me, all of the talks were good. There was nothing embarrassing about it, and so it was a very happy occasion, and I've been getting a lot of nice feedback. The interesting thing is that it was conceived not just to be an interesting meeting, but instead it was conceived as a catalyst for accelerated space progress before 2030, not just an interesting meeting. And I'm glad to report that this seems to be working even now. I was in Washington, D.C. 2 weeks ago, and there's quite a bit of ferment going on in certain high places that seems to have gotten people's attention. And of course, you never can tell what's going to happen in Washington, D.C., but it is encouraging up to a point. The name of the symposium is The Power of Synergy, and synergy was a new word invented about 50 years ago that combined the idea of synchrony, bringing things together, and energy, I think, or making things happen. And the basic idea is that diverse things can be combined so that the sum is much greater than the parts. And this applies to several things. It's, of course, to technologies, but also to the driving concepts and whatever institutions would fund changes and improvements and things. And so one of the fundamental things we're looking at is that traditionally in bureaucracies like NASA and Department of Energy, Department of Defense, and what have you, they all function and of course cover their own bases and fight for money. And the idea here is to try to find things that bring them together around a concept that's really important for the future, and notably for the future of the United States, because people like I am worry quite a bit about the developing competition from certainly China, Russia, and even other quarters. And if we don't get busy and start doing something in a hurry, we're going to find that we come up short. And so we believe that there are some wonderful examples of decadal change, and we just happen to be celebrating 3 of them right now, namely the 85th anniversary of the creation of TVA, which led to the putting a lot of people to work around here and transforming this region, but at the same time it led directly to the national power grid, which changed everything. At the beginning of the 30s, only about 20% of the country had electricity, and that of course was a complete transformation. 10 years later, the reason that the Manhattan Project was started here and most of the production that mattered was done here was because of that availability of the power from TVA. And that's 75 years ago. 50 years ago, down in Huntsville, which is burgeoned because of all the foregoing things, of course, is where the Apollo 11 was born and what got us to the moon. So we've got three important anniversaries, and then we've got a 50-year hiatus when nothing much has happened in space. And during that time, of course, the world has changed greatly from microelectronics and computers and all the rest, but we've watched our own technology base, our industrial base in this country has been winnowing down because of lack of interest, and I'm not in any way criticizing the progress that NASA has made in robotic exploration of the solar system, remarkable accomplishments, but the human presence in space has been confined to low orbit for 50 years. And we've learned a lot from the most expensive single thing ever built, namely the International Space Station. And one thing we've learned immediately from that is that you don't want to build things that take 20 years and more and are the most expensive things ever built. You have to find ways of doing things quicker, better, cheaper. Okay, well, let me dive into this and see what I can explain. First, I want to say that I've alluded to the progress that we're making already, and in large measure that's because we attracted some very interesting people to kick the thing off. And I was very pleased that the keynote address at the beginning on the first day was given by Morgan Smith, who is the CEO of Consolidated Nuclear Systems. He is in charge of Y12 and Pantex. He gave a marvelous talk. And on that subject, let me interrupt myself and say that the TVIW website, Tennessee Valley Interstellar Workshop, you can go to the home page and click on Symposia, and you'll see Power of Synergy Symposium. And then if you click on that, you'll find that all of the talks of all of the 36 speakers are there listed in order, three across, and so on. And Morgan Smith's talk is right up there near the beginning. And I urge you to take a look at these things. There's some really great and inspiring talks, and his is definitely one of them. The next keynote was given by John Vonglis, and we had gone to Washington twice before to appeal to the headquarters, Department of Energy, saying that what we're really here to encourage is developing nuclear propulsion in space, and Oak Ridge is where you should be looking at that, and that NASA has some fairly modest ideas about what you can do with nuclear in space, but we think we can do a lot better, and I'm going to try to show you why. Anyway, this resonated very well at ARPA-E, the Advanced Research Projects Agency of the Department of Energy, and at that time John Vonglis here was the acting director of that, and at the same time he was also the chief financial officer for DOE, which of course meant that he had to figure out what to do with about $60 billion, and that's not a bad situation to be in. I do want to mention too, on the second day, our keynote address was given by Alan Eisenhower, as the ORNL Associate Director for Nuclear Science and Engineering, And he gave very strong support to the idea of innovation and synergistic breakthroughs. And we greatly appreciate his interest in what we were doing across the board. Also, the fellow that was appointed by ORION to be our contact as we were planning this was Mark Uran. And some of you have probably heard Mark talk. And by the way, this Friday, he will be speaking at the American Museum of Science and Energy here in downtown and talking about the history of the space station. No one is more qualified to do that than Mark because he was at NASA headquarters for 28 years. And the last dozen years he was the director of the building of the space station. And so you want to hear it from the horse's mouth, that's where to go. Mark came here in 2012. He wanted to shift gears before he got any older and came to ORION. They put him in charge of being the contact with the huge controlled fusion experiment in France known as ITER, International Tokamak Experimental Reactor, I think it is. So my great thanks to all of them. Now, the vision that is driving all of this is that U.S. leadership is absolutely needed to achieve ambitious progress by 2030. And that means that we have to come up with robust, affordable systems and operations in order to develop the moon and the near-Earth asteroids and Mars. And these things are going to be the principal focus of the rest of my talk. The moon, it turns out, is really a key stepping stone for all of this and a heck of a lot more. And the elements of the power of synergy are very complicated, and I'm faced here with compressing ideas from 3 days of meetings, 9 hours a day, into 40 minutes or so. So I'm not going to show many slides with a lot of words on them, but this is just to give you a couple of slides at the beginning saying that in order to come out of this with a reasonable proposal and goals that we're now trying to sell, we have to look at concepts, technologies, applications, system planning, fiscal affordability, timelines, and then getting into the technologies. Really loud and clear finding from the whole meeting was that energy is the top of the list. We can't develop space and really realize the human potential in space without a lot more energy than has been considered in the past. It's not just a few big solar cells on the space station, which will get you a few tens of kilowatts, but we need to be talking megawatts and hundreds of megawatts and maybe even gigawatts in order to do things. And we certainly need to be talking about nuclear propulsion in space. There are other technologies that, and this is where synergy really comes in. Superconductivity is really trying to happen now, and whatever country takes advantage of that is going to have a transforming thing for the rest of the world. All of you are a little bit familiar with it if you've seen an MRI machine in a hospital. They happen to function as the way they do because of the superconducting coil that generates a very high magnetic field in the middle of it. And once you start the supercurrent flowing, it keeps right on doing it as long as you keep it cold enough to have the superconductivity working. High energy lasers is something that's been worked on for 50 years, and I was deeply involved in both superconductivity and lasers in my career, and they are ready to go. DARPA has matured them, the Defense Advanced Research Projects Agency, and we can now seriously talk about multi-megawatt lasers. 3D material processing, of course, right here in Oak Ridge. This is a world's leading place to be looking into that. And von Neumann machines are something that was John von Neumann proposed 60 years ago, machines that could replicate themselves and maybe even make little machines that make bigger machines and so on up. And you may say that sounds fantastic. I don't believe it, but you should talk to any woman. She can do it about once a month. And that is that this little thing that's 0.4 of a millimeter in diameter, 9 months later, can give you a beautiful baby. And 15 years later, it gives you a teenager, and you can worry about that. But the upshot is that micro electronics, MEMS devices, micro electromechanical systems, are mature enough so that you can actually contemplate things. That little ones can be put on the moon. They can start building bigger and bigger things, and this, of course, can industrialize the moon. To do all of this, what we did was create 4 themes, and each theme had its own chairperson, and we picked carefully the people and the topics that were considered. And the first one was concerned with large-scale space development in general, and the second, breakthrough concepts and technologies. The third, transformative decadal plan. How do you pull all this together so it can really have an impact? And finally, the ultimate path to the future, which is a fun thing. We got a renowned woman, Catherine Lazzaro, who's a great science fiction writer, but she also has a PhD in quantum physics from Harvard, and has made some significant contributions to thinking about how might we ever fly faster than light, if it is possible. So all of that was created and treated in depth by the various teams, and then at the end of the meeting we tried to bring it all together to get the recommendations. What I've done, I decided to do, since we don't have much time today, is to amplify a lot of things into theme 1, because it's the general theme that was kicking off things to look at large-scale space development and commercialization, how to do it. And theme 1 was chaired by John Mankins, who's a great guy. I've known him for over 30 years, and we worked together while I was at NASA headquarters quite a lot. He is a living expert on space technologies and how to carry them into the future. He gave a very good 30-minute opening keynote for his theme, and this is an important and interesting slide. It can everyone see that all right? The red pointer. The distance from the Earth to low Earth orbit. We're looking at the relative amounts of energy to make these transitions. From the Earth, just getting into low Earth orbit takes a lot of energy. Getting from low Earth orbit up to geostationary orbit, where there are now hundreds of active satellites worldwide, your dish television, and many other TV satellites up there, but they depend very much on international data processing, everything else, and not to speak of defense and intelligence. So there's traditionally been a lot of money spent getting there and a lot more money spent getting up there. Now, we're very happy that American industry and creativity is attacking that problem, and Elon Musk's Falcon 9 can be landed and reused, and Jeff Bezos coming on with his own versions of things are really changing things, so that the costs of doing things traditionally on the order of $10,000 per pound, just getting anything into low orbit, and more like $100,000 per pound to do things in high orbit. It's being dropped by a factor of 10 or 20 already, and there are ways of bringing it down even more. Musk is talking at present about $500 a pound, which is getting a little bit reasonable. But I don't know about you, it would still cost quite a bit to get me into orbit. And you notice, though, that if we get up to GEO, then getting to the moon is a trivial thing, very little energy required to do that. And you can even go to other planets and to Mars and rendezvous with Phobos and Deimos, the satellites of Mars, with very low expended energy. And you can do it really fast if you have nuclear propulsion. Instead of taking a year or more to get to Mars, you can do it in a matter of 30 to 60 days. And this is a very important difference. If you land on Mars, then you've got to get back up again, and so you're talking about quite a bit of energy there, and nuclear can help with that a lot too. But what it suggests is in the 10 years up to 2030, we might just have the objective of rendezvousing with the satellites of Mars, and they can be very important, as you'll see, if they have water in them, which they probably do, then that can be reaction mass to refuel nuclear rockets and so on. It can change everything about the difficulty of getting there. The synergistic integrated macro projects then that we focused on, both near and far term, the italics here mentions asteroid capture and industrialization. That's very important. Asteroid implementation of safe human travel is really mighty decisive in terms of everything, and safe lunar colonies and industrial development. Later on, what that implies after another decade is Mars and Jovian satellite travel and development that makes sense, and ultimately maybe being able to launch unmanned probes to the nearest stars. John Mankins briefly explained that he calls it HEADS, Human Exploration, Development, and Settlement. How to do it, you have to look at the affordability of everything you put together in the package, and how to ensure safety and reliability and effective and extensible missions and systems that go with it. And he's generated many fun concepts over the years, but this is kind of an example. If you look carefully, you can see a human being in there in this habitat. This has been built with these machines that started by taking dust from the moon and producing the components of this so that you could manufacture these. And you see that John has named it Conestoga, which is the name of the covered wagons that settled the West. And a bunch of them have circled their wagons down here. I'm not sure if aliens are about to attack or what. John also has made a very strong case, and we'll come back to this a little bit later, for being able to manufacture large systems in space that have all kinds of applications. And in particular, he's focused on the generation of electric power from the sun and then beaming it either with microwaves or lasers to the ground on the Earth or to other objects in the solar system, including the moon. After John's opening talk in Theme 1, our first speaker was Franklin Chang Diaz, who talked about living and working in space from an astronaut's point of view. He's fully qualified to do that. He flew on 7 different missions and spent a total of 66 days in space, the second longest of any American. At the time of our meeting, he was in Japan, got up at 1 o'clock in the morning, put on his tie and suit, and talked to our group for 30 minutes on Skype, and we had a great link back and forth. The things that he said were very encouraging, and it focused the meeting on the fact that this ain't going to be simple. We've got a lot of things that were learned from the space station over 20-25 years, but we're still only 70 to 80% closed cycle. They're still throwing the waste down and letting it burn in the Earth's atmosphere, and we have to go back and supply things, including oxygen and other things. So to have permanent colonies on the moon and beyond, we certainly have to have fully closed systems. My remote is never working. I have to remember to push this button. The second talk was about Jim Powell, and Jim is now 85 and fighting the battle with cancer. He wasn't able to come to the meeting, but I've worked with him for about 40 years and have the greatest respect for him. If we had national living treasures like the Japanese do, he would be one of them. He made his career at Brookhaven and was one of the great innovators of innovation for reactor design and for many other things. And he actually got into superconductivity in 1968 and proposed superconducting maglev. And that has so many implications. You see in the background here, one thing you can do with it is launch catapult things into space, so you eliminate the first stage of the rocket, and we can go on from there. I like to show just a minute or two of a movie because Jim was actually the inventor of the concept of superconducting maglev trains, and of course nothing happened in the United States during that 50 years, but the Japanese waited until the patents expired, and then they've thrown in quite a few $1 billion to mature the fastest train in the world. What you're about to see is a movie 16 years old that I'll just let it run for a minute or two here so you can get the flavor of it, because it pertains to, of course, catapulting and everything else.
In December 2003, the superconducting maglev set a new world record in the railway industry with a manned speed of 581 kilometers per hour at the Yamanashi maglev test line. Running tests on the 18.4-kilometer priority section of the Yamanashi maglev test line were begun in March 1997. The superconducting maglev produces far less noise and ground-borne vibration than conventional high-speed trains. And since the maglev runs by levitation 10 centimeters above the U-shaped guideway, it has a high level of safety in the face of earthquakes at high speeds. These characteristics make the maglev an ideal solution for the large volume, high-speed transportation needs of tomorrow. The superconducting maglev is superior in its ability for acceleration and deceleration. It can accelerate to a speed of 500 kilometers per hour in only 5.7 kilometers, while Shanghai's Transrapid requires 17.8 kilometers to reach the same speed. The superconducting maglev would cut the journey time between Tokyo and Osaka to about 1 hour and carry 1,000 passengers. With 10 trains each way per hour, or 200 round trips per day, the trains will be able to carry 200,000 passengers daily.
I'll stop there, but I think that makes believers of all of us, and that was 16 years ago. They have fully matured the technologies, and we can use them now, and it's a simple thing to scale from what they have done to what you see on the screen here. This catapult launcher could be built within the precincts of the White Sands Reservation, and there's a nice high mountain right in the middle, 12,000-foot peak, and you'll get a shock wave, of course, when the thing comes out there at about Mach 8. But it goes straight into space, and this, instead of costing $1,000 or $500 a pound once it's built, it costs less than $50 a pound. And so this can open up space for unmanned payloads that are very, very cheap, and this is truly important for certain things. We may make an end run around it ultimately, if we can manufacture things, say, from moon dust and asteroid dust. But the The fact is that Jim came up with the Star Tram concept, and we know how to scale this for human launch too. You've got to have a much longer acceleration tube so you don't exceed about 3G, and ultimately it can carry people into space for a reasonable amount of money too. Other than the superconductivity, though, what is really crucial for what we're talking about now is that Jim was also the inventor of the particle bed reactor. And this was after 60 years ago, in the mid to early 60s, we were so enthusiastic about everything nuclear that we thought it would be very easy to go on and build a nuclear rocket that could take off from the Earth and so on. And the NERVA system, the Kiwi systems were built and tested in the Nevada desert and even deliberately tested to destruction. And we learned a great deal from that. But about 1970, when the anti-nuclear panic, whatever you want to call it, came into vogue, then people lost interest. It turns out that you can launch uranium, enriched uranium, on a rocket into low Earth orbit with no fear whatsoever. If the reactor has never been fired up, it's totally safe, and even if it blew up on the pad, you wouldn't have any problem with the residual uranium. But that, of course, didn't carry the day back then. The two things you see in the picture here, that was a model of, you see the particle beds here. Now don't confuse it with pellet bed reactors, because here we have very, very small particles, about half a millimeter, that have about 0.2 millimeter sphere of uranium in the middle and a refractory coating around it. But as you know, when you divide things up into zillions of little points, they have a huge surface area. And so it maximizes the heat transfer, and you put the liquid hydrogen in here, it passes radially in and is heated from super cold to 3,000 Kelvin, just passing through there, and it comes out the nozzle here. And then as it is scaled to a reactor design, you see each of these cylinders is one of these, basically, and so you can cluster them. And a program developed, and it started in 1968. It was highly classified, developed by DARPA, and it was called Timberwind. And after the Cold War ended, most of it, the technology was declassified pretty much, and only the mission remains classified now. You can even go to Wikipedia and look up Timberwind and get a story there. It's the performance that's quoted isn't quite right, but other than that, it's very interesting to go to the website of BWXT, which of course is what Morgan Smith runs at Y12. And if you read, I'm going to read that to you. It says that this is on their website now. As far as I know, it's still there. In 1987, BWXT received a contract to design a space nuclear thermal propulsion system in support of the U.S. Department of Defense SNTP program. The program sought to develop a lighter and smaller second-generation PBR-based nuclear rocket. While the program ceased at the end of the Cold War in 1993, the PBR was extensively tested and validated, signaling a giant leap forward in the size reduction of nuclear propulsion engines. And this is really true. This is a gigawatt reactor, and the total system, including the pumps and everything, weighs about 700 kilograms. And think of that, the reactor itself could sit on this table, and the performance of it is more than twice that of any chemical propulsion system, and all it needs is a reaction mass, and hydrogen is the best. You could use water instead. Okay, well, time's moving fast here. I've got to pick up speed. What I did was to focus on the last talk in theme 1, which was by Joel Sercel, and it's really a fabulous talk to watch if you can go to that website. And by the way, after that, at the end of themes 2, 3, and 4, you will find a panel discussion where they review what was learned and what the opinions are, and that's what converges on the ultimate findings of the meeting. At the end of theme 1, we didn't, but right now I'm going to reach into the future themes and bring them together to just give you a working example of what the power of synergy is all about and how you can visualize it. Joel Sercel is the leading expert, I would say, on how to capture asteroids and industrialize their materials, and you'll find a detailed discussion of all that. I'll come back to this slide in a little bit, but this is, when people think of asteroids, they normally think of this belt between Jupiter and Mars, but you don't see much in here. The blue orbit is the orbit of the Earth, but it turns out that that's very misleading. These were all discovered early because they're reasonably big, but collisions among them for 4.5 billion years have generated a huge number of small ones. And so Joel presented this graph, which shows the cumulative counts, and notice many orders of magnitude going up here, and you can consider it the size of the object coming here. This is objects that are 1 kilometer in diameter, 100 meters in diameter, 10 meters in diameter, about the size of your house. And the message here is that as you go from 100 meters up to that, you're 4 orders of magnitude more. So there's very good reason to believe there are about 100 million of these 10-meter diameter objects that are in Earth-probes and nearby orbits. And it's okay in terms of a threat from ones this small. Literally, one of them passes, here's the orbit of the moon. If you think of a sphere the size of the moon's orbit, one of them passes through every day or two. And occasionally they get randomized. If they come close to the moon, they wander around sort of trapped and then go away. And if you look into it deeper, there are other places you can find them that have very low relative velocity to the Earth, and that makes them easy to capture. So the question is, how can we industrialize and commercialize development of near-Earth asteroids? And the synergistic concepts are, we got to capture the small ones and do in situ material processing and rapid commercialization to make them pay for themselves and make everything affordable. And to capture them, when we do capture them, they have very useful materials, and that can be used for radiation shielding and solve a very major problem of human presence in space. Basically, you can think about the fact that right now the space station has a balloon-type habitat that was built by Bigelow Corporation, and it's reasonably large, and it's been attached to the station for a couple of years. The astronauts can get inside it and so on. Now, think instead of 2 balloons, one inside of the other, with about 2 feet between the inner and outer one. If we can capture an asteroid, get the dust from the asteroid, and put a spherical layer around it, then the humans inside of this thing are protected from solar flares and cosmic rays just as well as we are in this room right now. The 2 feet of asteroid dust is about a shielding that would solve the problem. And that's what this slide says, and so I won't dwell on it. These things have been well known for a long time, and I particularly like to show this old picture from 1972. from a movie that was taken at Jackson Hole. You see going over right there, a 10-meter or so object was grazing through the Earth's atmosphere at a height of 40 miles, and it was observed by Air Force radars from space, and by judging on its deceleration and so on, it skipped back into space, but they were able to estimate its size. And a lot of people had movie cameras. You see this one tracked it for about a minute or more, and you can see it passing over the horizon there. This is a picture of the very first near-Earth asteroid, and it's a big one. It's about the size of Manhattan Island, 10 or 12 miles long, Eros. And in 2000, NASA landed a probe on it. These pictures here were taken as it was approaching. And you notice there's a crater on the backside and a blowout on this side, and the whole thing was distorted into this shape. So the lesson from it is that it's actually a rubble pile, and as it got down under a kilometer before the landing, you can see the surface boulders and a lot of dust. And so even when we scale down to the small ones, only 10 meters in diameter, we can expect that about 80% of them are going to be similar composition. A few of them, maybe 2 or 3% at most, are metallic, and their core material, probably from a collision with Vesta, the third largest asteroid, a long time ago. And the one that crashed into Arizona 50,000 years ago happens to have been one of those. They've recovered the metals and so on. And before the modern times, everyone thought most meteorites were metal just because they survived, and you can still go to Antarctica and pick them up, you know. But they're rare. The real common ones are just rubble piles. And about 20% of them are carbonaceous chondrites, which have not only carbon compounds in them, but also a lot of water. And the fact that they've got a lot of water is really important, and Joel Sercel's talk really will fill you in on all of that. So if we want to utilize these things, the essentials are to find them and get to them and tame them. And I've already talked a little bit about their presence, but there's one interesting thing in this picture. These are real data of thousands of objects, and here's Jupiter here. And you notice, can you see the little fine sprinkling of asteroids there, and another one up here? And these are at 60-degree angle with respect to where Jupiter is, but they're large volumes. This was predicted about 250 years ago by the French mathematician Lagrange, and they're called Lagrange points. And you can see that here is the Sun, the Earth, and we have an L4 and L5 region on our orbit where similar trapping to what you saw at Jupiter is probably occurring, and it's already been found on the orbit of Mars as well. A few asteroids are there. Now, it turns out that the same thing is true just for the Earth-Moon system. If instead this is the Earth and this is the Moon, then there are these L4 and L5 regions on the lunar orbit. And so if we can snag a passing asteroid and get it into these regions here, it's permanently trapped and gives us plenty of time to work on it. And also we can nudge it into orbit around the Moon and keep it in the family, if you will. Detection of these things is difficult. We need an infrared satellite between the Earth and Venus looking back in this direction so we can see them coming. And the problem with radar is that it's an inverse fourth power thing. You lose inverse square going out and then the reflection coming back. And so you can't search the whole sky fast enough to catch these things before they pass by. But now that NASA has got satellites in the, not satellites, but spacecraft out at the L1 point between the Sun and the Earth, looking back here, it not only sends these beautiful pictures of the Earth every day, but it can also search the small asteroids. And when they are found, then you can put radar on them, and what you get is really nice. This is a radar image of a near-Earth asteroid that was taken from JPL, and this is over a period of about 8 hours. You see it's like flipping a tennis racket into the air. It has 3 different axes of rotation, and that, of course, is something that has to be dealt with, but fortunately they're pretty slow. It might take 4 hours for one revolution. Now, we're talking about synergy, and here's an amazing thing. The superconductivity that we've validated for lots of propulsion applications is easy to do for a coil of wire that doesn't weigh very much. And so Jim Powell and I worked with him on it, came up with MIC, which is magnetically inflated cable, for making large, very lightweight structures that can do all kinds of things. And in particular, I want to show you what we can do if we have a MIC concentrator to capture these asteroids. And the way we do it is this. The proof of principle experiment was done by Ampere in 1835. Your amps are named after him. And what he learned in the early days, he had a battery here, ran current down a wire and back up the other side. The wires bulged apart because the magnetic field was opposed, as we call it the right-hand rule in physics and engineering. And so if you have an appreciable current flowing in a loop like this, it wants more than anything to spread out and be a perfect circle. And that means that we can have 3 of them, one here and another one here and a third one out here. And by just energizing the coils, then the thing will deploy itself, and it can be really big. This is 100 meters in diameter, which means that if we point it at the sun, we'll get about 10 megawatts at the focus at 3,000 degrees, and that's a nice thing to do. So this is a payload that will fit on one of Elon Musk's Falcon 9 rockets. It's about 4 meters, I think, in diameter. And here's what happens if you have designed your deployment system for the solar concentrator. Those are carbon filament that help shape it. Nice and big. Okay, now if you've got it, and if you've got your nuclear tugboat that can take off like a scalded dog if you discover a 10-meter asteroid you want to snag, then you use that to push this thing into the neighborhood, and you ask it to do the job. So it manipulates until it's nearby, focuses the energy on the asteroid and turns it into a rocket. And by deftly doing this over a period of 4 or 5 days, you get it to propel itself into one of the L4, L5 regions around the Earth, and you got it. And it turns out, we've published papers on this and so on, but the looking at the mass that you evaporate from the asteroid, it depends on the relative velocity. If it's only 1 kilometer per second or 5 kilometers per second, of course you'll need more energy to trap to subtract the larger velocity. But we've got the required energy, the mass evaporated, the volume removed, and the volume remaining, and the mass remaining, and the required time to do it. And so what you see is between 5 and 15 days, you can have, from capturing one of these objects, you can have close to 1 million kilograms of material, or down to 250,000. That's a heck of a lot of material. Think of how difficult it would be to bring that up from the Earth or even from the surface of the moon for that matter. And this is a way of getting a free lunch. We could just by using sunlight and nuclear propulsion to get you there, you have this energy that gives you all this material that you can industrialize. And these are some of my own concepts, and Joel Sercel has some really complicated ones. But here I've got the nuclear rocket is here. These are very lightweight things. They're buckyball type structures with membranes, and they're there to capture the material as you work on the asteroid. And you can see it from different angles here. And as it approaches, it telescopes out to fit the asteroid you're approaching. And so back up one knot, and you see you come together like that. And now you can focus more energy in there, or use grinding tools and whatever to recover the solid material. And you can also catch the water vapor and other volatiles that come out and put them into tanks. So I've mentioned briefly the shielding from radiation, but it turns out that if you can do this, and if you can do the inflatable thing and make habitats that are affordable and easy to do, then you also can solve the problem of long exposure to low gravity in space. And one of the experts on that is Ken Roy back in the back of the room, who gave a great talk on it at the meeting. And it turns out that the correct way, the easy way to solve the problem is like this. You have two asteroid products, one here and one way over there. And I have a tube connecting them so the astronauts can travel back and forth. Maybe you have a garden over there to grow the vegetables and the people in here. And the lander for Mars is right there in the middle. So here's what happens. It's revolving about once every 2 minutes. And the centripetal force is creating artificial gravity inside. And so with that kind of revolution and 500 meters between them, you're generating something a little bit more than Mars gravity. So instead of being weightless and having all kinds of physiological problems from long exposure to weightlessness, they'll be comfortable. And you can think of having a whole bunch of these things around the orbits so that they osculate the orbit of the Earth and Mars, and so there'll be a convenient one every month or two where you hop on board here and get off when you get to Mars, and so on. I'm already getting short on time. I want to mention von Neumann engineering. I mentioned earlier the idea of small electromechanical devices building bigger ones, but this is really important in terms of economic commercialization of the moon and asteroids, is that if you have the machines that can do what you tell them to do, then they can manufacture all kinds of valuable products, including structural components. I'll just skip ahead of that. One thing about that is that it's we've got the wonderful work that's being done at ORNL over the other side of the bridge here with 3D printing and augmented manufacturing, and that can easily be focused. We did get the fellow who was running that program to give a talk at the meeting, and so we ought to be doing experiments now, kind of university level experiments to develop the processes, and this can all be done pretty readily. Now, finally, I want to race through themes 2 and 3 and 4. Most of the technologies, and a lot of which I have not mentioned, were exposed and developed in Theme 2. And we had a great guy running it, Jason Derleth, from NASA headquarters. And for the last 8 or 10 years, he's been managing NIAC, which is NASA Innovative Advanced Concepts. And as you see there, what it is a program to support early studies of innovative yet credible visionary concepts that could one day change the possible in aerospace. And Jason's a marvelous guy, and he, among other things, has hobbies, and he carved his own cello, and it's a good one. And when I introduced him at the meeting, I said it might even be valuable 500 years from now. He has on his website this kind of compelling view, which is maybe 1,000 years in the future, but it's inside of a donut, a toroidal space habitat, and it can have landforms and cities and weather and all of those things, and he's reaching out for what we can really do. There's enough material in all the asteroids. If we really got good at what I'm talking about, you can develop things like this with 1 million times as much habitable area as all the continents on the Earth. So some of us view the open-ended future of the human race in things like this. The next talk in Theme 2 was by Jonathan Witter from BWXT, of all things, and he is one of the living experts on the development of the particle bed reactor. And this particular chart that he showed, it's too small to read, of course, here, but it runs from 1960 up to the present. And he has the NERVA experiment there in the beginning of the particle bed reactor here, and all the way up to the picture I showed you of the current website. But what he's saying is we know how to do this, and DARPA experiment has already shown us. DARPA put $330 million over a period of 5 years into substantiating everything I'm claiming about that. And so it's real. And I won't belabor this. This is one of the 400 micron diameter particles with the uranium in the middle, and you see them clustered here, and this is showing the moderators and the flow of the cold gas in and the hot gas coming out. The particle beds are here. Now the next talk in Theme 2 is also very exciting. Phil Lubin is the living expert on this. He's at University of California at Santa Barbara. But what he also is serving as the technical leader for the $100 million Starshot program that the Russian entrepreneur who's now living in England, Yuri Milner, has funded. And they've been looking primarily at how do you launch very lightweight small probes to the nearest stars. But for purposes of our meeting, what he did was to scale it down to our solar system. And he's looking here at the payload mass ranging from 10 kilograms up to 100,000 kilograms, and the different travel times of the things from the Earth to Mars, and the different laser powers that are needed to accomplish that. And so it's all parameterized, and what you find is really fascinating, because you can launch payloads of 1,000 kilograms, which could be a lot of food and maybe the medicine and the brandy for that was formerly carried by the St. Bernard can be instead delivered to the spacecraft on the way to Mars if you need some support in a hurry. And all you need to do that is a gigawatt array of lasers, either on the ground in Chile or on the moon, and they can propel a laser cell, not a solar cell, craft that can make these really fast trips. And Phil ended his talk with this, saying that humanity's first interstellar missions will ride a beam of light. And indeed, they have really demonstrated the feasibility of this. I actually published a paper on it in 1975 for JPL. I was thinking along the same lines way back then, and we tried so hard to get megawatt lasers going, and now it's a comfortable thing that I've lived long enough to see it. Okay, the next talk after that in theme 2 was by Robert Begdigian from Marshall Space Flight Center, and he's a living expert on how do you build the systems inside of a human habitat to keep the air and the sanitation and the all the recycling systems working. And he gave a very interesting talk on that. This spacecraft here is something that NASA is looking at putting at the L2 point beyond the moon. Now they call it the Gateway concept. And among other things, it's interesting that they have an inflatable like that built by Bigelow in the concept. Also, Begdigian's talk, he went into details, and again, Ken Roy back there can talk to a lot of these details, but this is talking about carbon dioxide and oxygen recovery, and what is it? I can't even read the slide very well myself. This is urine and humidity coming back around and being recycled. And so all of these things, of course, have to work together in a perfect way to sustain humans for long periods of time, either at a moon base or on traveling to Mars and getting to Mars. This is Bill Peter, who is in charge of a lot of the 3D operations for ORION, and he gave a talk talking about the abilities to evolve from what we can do and have proven every day out here to what we need to do in space. And then this unknown character, Ken Roy, gave a really neat talk about the solution to low gravity physiology. And he looked at all of these things, bone loss and muscle loss and inner ear problems and visual things, spine, immune system, sense of taste, and the drugs that act differently on the body. And he came up with the idea of centrifugal devices even on the surface of planets or satellites to solve the zero gravity or low gravity problem the same way that I was talking about having the asteroids revolving around. But now think back to the Japanese train using Jim Powell's maglev technique. And those things, when we say they're superconducting maglev trains, the superconductors are all just in the moving vehicles. The coils that support them and propel them are just aluminum coils, and they're cheap, and you can bury them in the soil. Well, Ken would have us believe that you can have them around the rim of a crater about a mile in diameter, and we can build these vehicles that have people in there that can have their lives inside of these things, and you can make more coils so that they can peel off and come to a stop and then reaccelerate to come in. And it doesn't have to maintain any particular balance because your centrifugal force is just pressing against the wall of the crater. So there may be a very simple way if we decide to put a colony on the moon or a settlement, and so we picked a nice crater about a mile in diameter and have this propulsion system powered by sunlight that has these things coming around, and as we get more and more people, we just put in more and more of the vehicles, and eventually they make a full torus, and we can build on that. Then we got to theme 3, which is how do you put it all together into a decadal plan, and have a great guy running that, Matt Hollingsworth. He worked for me for a few years when he was still working on his master's in physics at UT. He went to CERN 4 times to help with the Higgs boson search. Came back, he formed a company with a Swiss guy over there, decided he wanted to go into business, and so he was admitted to the Super MBA program at Stanford, and was there for 2 years, required coming out of that to create a new company, which he did, but by then he'd gotten to know a bunch of angel investors in Silicon Valley, so he got $10 million to start his new company, and he was with me 3 weeks ago, in Washington because he was signing a $200 million agreement, open-ended per year, to make this a way of streamlining healthcare and making it easier on the patients to know what's going on the government to get fair charging. And it's something that obviously needs to be done. But Matt's real interest is in space. He's a great believer in StarTram, the electromagnetic launch, and he's only 31 years old, and I think he has recognized the talents of Jeff Bezos. I'm betting on him in another 10 or 20 years. But he has come up with the concept of creating what he calls nucleation laboratories. And he's very aware that innovation has been stifled in this country by what's called the Valley of Death, between when you do creative things and even patent them, and most of the people with money are just concerned about industrializing it. But you need about 10 or $20 million in the valley between in order to make that happen. And the same disease has infected the national labs. I mean, you try to go out here, it used to be that they really encouraged companies and put support in, but now you have to get money, a few million, and prove you've got something, and then they're glad to talk with you. And that has to be fixed. And what Matt has come up with is his nucleation labs, which he's modeling after Bell Labs. And Bell Labs, as some of you know, when AT&T was the largest corporation in the world, they built all the telephone companies first in the United States and then around the world. They had plenty of money to build Bell Labs, which was one of the greatest things ever done. It was very much like a national lab used to be, and it was located in New Jersey. And, Matt begins his pitch by pointing out that 60 years ago, Bell Labs invented what is now recognizable as 50% of our gross domestic product. And what he is pointing to is that all these things, transistors, texting, movies, digital computers, lasers, solar energy, satellite communications, mobile phones, and even understanding the universe, all of that started at Bell Labs. This understanding the universe, of course, was the discovery of the cosmic background radiation, the 3-degree thermal background. And so what his nucleation labs are is doing the same thing, get money from angel investors, have one in the east of the U.S. and one on the west coast. And he loves Tennessee. He was born in Dandridge, loves the University of Tennessee, so I hope he's getting really enthusiastic about putting one of these labs here, and that's going to have great consequences for us. The next talk in that theme 3 was given by this unknown character here, and we've already discussed that. John Mankins came back, the theme chair from the first, and he told about his concept for developing solar power in space. And basically, you replicate the same machines over and over again, which are about the size of your dishwasher, and they are smart enough to gang together and station keep and even lock with each other so that they can become the solar power thing, and they have the ability to beam microwaves down to the ground. And he feels that this can supply power around the world very cheaply if we can manufacture the things in space that can do it, just turn it loose and it builds one after the other. So all of that is in his discussion, which you can go to the website and hear in theme 3. And then Dean Hartley III, who was my co-chair at this meeting, a great man. He's got a deep background in math, PhD in math, but he's best known for his work in systems analysis, and he has won several national awards for that. He's been vice president of the Defense, what do they call it, MORS, Military Operations Research Society, and he was very, very instrumental in helping everything that we did to happen. And here he gave this talk at the end of theme 3, telling how do we integrate all of this, and he looked at it from all these different points of view, which you can probably read: integrating safety, integrating infrastructure, testing technologies, looking at sites and purposes, and computational systems and the environments. And then he gets into the details of the technologies, and so all of this was what was required to come out of the meeting, with some explicit recommendations that are good enough so that they're getting people's attention. They're listening to us. Okay, and then finally, theme 4 was really fun. Catherine Asaro, who is a great writer, she has written very, very fine science fiction, and I've read everything she's written. I think her saga goes on for about 15 volumes or something, but she published an important paper in one of the physics journals about 15 years ago about her perceptions of how to go from state of knowledge of quantum mechanics to thinking about possible faster than light travel. So we had also Ruth Kastner, who is a very cutting edge type quantum physicist, who gave a talk in support of that. And we had talks by 5 other science fiction writers, all of whom were quite famous, if you know about that. And Catherine finished theme 4 with this: stepping into the future, will we remain humanity as we know it? And by then, all these things had been brought up about robots taking over for us, and whether we can modify the genome and become something we're not. So it was fun, it was great, and I do hope that it communicates for a long time by way of the TVIW website, and I sure would like feedback from all of you. Excuse me for running this far over time.
John, thank you. We have time for some questions.
Okay.
And that's all right with you. So, would anyone like to give John a hard time? Larry.
Yeah. Jupiter has leading and trailing Trojans. A lot of the gas giants have leading and trailing Trojans. The Earth doesn't seem to have so many. So how do we go about keeping them if we do capture them?
Well, there are several answers, and that's a good observation. The first is that we really don't know that, because we haven't sent a probe 1 AU along our orbit in either direction. And as you saw, they're not just points, they're huge volumes of space. And so it's quite logical that since that curve is so steep, and as you go to the smaller and smaller ones, they're harder and harder to detect. And so you're not going to find them unless you get over there and do it. But in spite of all of that, that's for the future, and it would be wonderful if we can, and we can certainly go to either of those volumes. But we know for a fact, from just observing what's happening every day or two, that at the tail end of the velocity curve, most of them are kind of co-rotating around the Earth's orbit in the same direction. So it's not uncommon to have relatively low velocities, and even sometimes they're perturbed enough by the combination of the Earth and Moon that they wander around in the L4 and L5 areas on the lunar orbit for days or weeks and then escape again. And so I don't think there's much problem arguing that we have a lot of resources there. Yes, sir.
How effective is this treadmill that the astronauts can run on, holding on to springs to load the skeleton?
The answer is it doesn't do as well as you would like, and I believe Ken back there, you want to answer that, Ken?
Well, yeah, it kind of falls in the category of something is better than nothing. And if you do nothing in 0G, there's a lot of bad physical effects. So this is an effort, that's one of many things that NASA is trying to do to try to keep their astronauts healthy, and they are making progress. It does help, but it's not the answer, and it doesn't do as much as we would really hope.
The body itself doesn't have weight, and I guess the problem is you can exercise the muscles, but the hydrostatic equilibrium throughout the body is still disturbed, and that's sending all kinds of messages to the autonomic nervous system that it doesn't quite know what to do with. And so there we are. Yeah, David.
John, have you had much response from Bohr, Hill, and Y12 saying, well, we really need to take what's done here and push a little bit harder?
Not enough yet, and we're aware of some of the bureaucratic problems there.
I know you get a good response from in Washington.
Yeah, and in my long experience in Washington, I was there for 22 years, and only the thing that gets a response is top-down requests, quote. Yes.
If you have one of these kind of soda devices there, and you're going to build those on an asteroid, is that correct?
No, on the surface of the moon.
On the surface?
Of the moon, yes.
Oh, it's on the moon?
Yeah,
Okay.
and the same thing could conceivably be on the surface of Mars. And they could be, yes, we could produce things like that in space from the asteroids, but they wouldn't need to have the walking and all that.
What composition of materials do you need? Those are going to be metallic structures?
Yeah,
Carbon composite?
the talk by Joel Sercel, talk 1.5 in theme 1 really addresses your question beautifully, and the materials that are available in the asteroids are pretty much the same that are available on Earth, and so it's just learning how to process them, and this is of course where the need for large amounts of energy come in, because you've seen what you can do if you just focus sunlight, and so if you develop the machinery that can take these things and refine them and make them into structures, then it all happens.
That would be technology that we already have. We're going to transfer it up to the moon.
Absolutely,
Build something there
yeah.
from concentrating sunlight.
In many cases that is true. Some things in space can be a lot easier than they are on the Earth, and particularly with free energy from sunlight, focused energy.
Big magnifying glass.
Yeah, that's right, exactly.
Well, John, it's delightful to hear some of these things. We usually present our speaker with commemorative Orion Cup, and then we decided not to because some people had them.
Oh,
And so you don't get one. On the other hand, this is a new design. So
well,
you've got the first one.
oh, thank you.
You have a picture, John? Get it back. How did you get it back?
Well, I get it. It was-
Okay. Okay. So
Are they supposed to put a quarter in here when they're leaving?